Welcome. Thank you.
Yeah, good to be here. Thanks.
Yeah. No, thank you. We the podcast and Twitter game is super funny. I think overall, a lot of the blockchain, not debates, but like talking points, are super hard to like narrow down on Twitter. It's just like quote tweeting or retweeting or I don't know, just going back and forth. And so I really appreciate you coming on the podcast and willing to chat, Nick. So thank you. I'm excited for the conversation.
Yeah, me too. I mean, recently there was like a really long Twitter thread where we were debating tons of stuff like settlement layers. And I think one of the reply trees got to like 260 or something.
Oh, really?
Yeah. And I mean, it's just, I think sometimes you end up just talking past each other on Twitter because, yeah, I mean, there's only so much you can fit into 280 characters.
For sure. No, it's super hard on Twitter. Like, I mean, the more long form you have, I think is the better because, I mean, a lot of these, especially in like blockchain and crypto, the devil's in the details. And so it's very hard to get into the details within 280 characters. So being able to talk about it long form and get into the nitty gritty and even just explain like, I mean, your technical depth, and then break apart the smaller components, I think is vital. So
yeah. And also I think for a lot of people that jump into crypto, you know, they don't start from first principles. And so I think that's also a really big thing. And even for me, it's taken me a long time to actually realize what the true first principles were, because I think there's a lot of sort of misconceptions out there.
I fully agree.
And so, yeah, hopefully we can.
No, I think that's a great jumping off point. If I'm a maxi of anything, I'm trying to be more of a good vibes maxi and then a first principles maxi. So
you can't go wrong with
exactly.
that.
So maybe to kind of kick off the conversation, how would you describe Celestia kind of in your own words? And then maybe from there, talk a little bit more about like the modularity of it.
Absolutely. So Celestia is the first modular blockchain network. So its core insight is that if you go back to first principles of blockchains, you realize that every chain since Bitcoin has followed one specific design pattern, which we call monolithic blockchains. And that's where the protocol does every single function that is necessary to power decentralized applications under one roof, within one protocol, using one set of nodes or validators. But a modular blockchain it takes the insight that actually you can break those functions into separate layers, and each layer can be its own protocol, like its own blockchain practically. But then those blockchains are stacked back on top of each other and recomposed to produce the same functionality, but actually with dramatically better results. Like it's more scalable, it's more decentralized, you have more flexibility. And you have something new called sovereignty, which we can also talk about. But the core thing is that modularity is sort of like, it's a new paradigm that we're trying to bring to the world so that Web3 can actually reach its full potential.
No, I think that's excellent. And for the people that don't know kind of like the individual parts, maybe start with articulating those and then how they are separated in their individual components versus, say, a monolithic blockchain.
Mm-hmm. So it's tricky because a lot of people, you know, when they learn about blockchains, they just assume that the miners or the validators do everything. And so they don't even think about some of these layers as separate components. But the components are first consensus, then data availability, which is also very sort of misunderstood or not commonly known property. So we have to talk about that a little bit more. Settlement, and then execution. So consensus is the layer of the stack that is just responsible for ordering data. So if you're trying to build a sort of distributed like state machine replication thing, the first thing you need to know is like, well, what is the ground truth? Like what do we agree has happened and in what order? Mm-hmm. And so that's all the consensus does, is it basically just says, this is the order, and we all agree on it. No matter what view, no matter what node you are on the network, we all are seeing the same thing. Then is data availability. Data availability is this concept that in addition to having an ordering over data, we need to make sure that that data was published to the network. So it's available. Anyone who wanted to could download it. And this is a super nuanced and confusing thing, so we can go deeper into that. And it's also, a lot of people say data availability is not a problem that blockchains face. And that is true insofar as if you, well, let's save that for later. But basically, it becomes a problem when you want to scale blockchains without sacrificing decentralization. So the next layer is settlement, which is actually kind of a optional layer, but essentially settlement layer is like a place for execution, which would be like rollups to post updates and resolve conflicts and like verify proofs. And then of course, execution is essentially where applications live. So it's where you'd have smart contracts. It's where you'd have users transacting with each other, DeFi, NFTs, DAOs, and all the different use cases that people envision. And so then they're all basically stacked kind of vertically in that order. Although it's not like they're all stacked on top of each other. They all kind of like are different components that can be recombined how you want. So the developer has like the flexibility to choose among those components.
And the main difference between the monolithic blockchain and Celestia is that Celestia has the ability to ultimately break apart those, where monolithic, you cannot break those apart. They're just kind of set standards within the individual monolithic blockchain.
Yeah, so the monoliths basically do all of that within one protocol. And they also set those standards themselves so that you can't, for example, like if I'm building on Ethereum, the people who designed the Ethereum protocol have sort of made choices for me that I, as a developer using this protocol, can't escape from. So like, one big one, probably the one that's most important, is that they have chosen, a certain version of the EVM that is going to be sort of the canonical virtual machine that everyone runs their programs on. But there's advantages and disadvantages to any given sort of like programming environment. And so people might want to actually build on something else. Like Solana has sea level, or, some more like WASM based thing. Like there's, a hugely, I think, underexplored, area of like different execution environments that can be run on blockchains. And so that's one of the first things that the modular paradigm breaks wide open, is like, you're actually not locked into any execution environment.
No, I agree. I think it's wonderful to be able to explore all the different execution environments, and I hope we can go more into depth on that later. But I think maybe just sticking with the separation of these different topics for the moment, maybe diving deeper into the data availability, because you said that is probably the most confusing part within the entire stack.
Yeah. So data availability, as I said, is trying to solve the problem of how do I know that the data behind a given block in the chain is available, meaning that it was actually published to the network. And in order to understand what this means, we kind of have to like go deeper into how blockchains work. So usually when you come to consensus, when a new block is published, it's just a block header, right, with some metadata, and then a state root and maybe like a transaction root or whatever. And so the point is that that block header doesn't actually contain all the data of the transactions. But in a normal blockchain, every full node and every validating node downloads a block header and all the transaction data associated with it, re-executes all those transactions, and then makes sure that it lines up with the data that was committed to in the block header, if that makes sense. So every full node in a monolithic chain downloads all the data, re-executes every transaction, and then says, okay, check, this is okay. Now, that is a fundamentally the scalability of any protocol that follows that is fundamentally limited, because each node, if you want to, let's say now we want to increase the number of transactions that we're going to process in a given block. Mm-hmm. Now you increase two things. One is the node has to have more bandwidth to download more data.
Yep. So in this scenario, you're increasing the block size?
You're increasing the block size, right? Why? Yeah. So like, why is that not a viable way to scale? Because if you increase the block size, like the number of transactions in each block, essentially, then you need to have more bandwidth to download more transactions. Then you also need more compute to basically be able to re-execute all those transactions and verify the block. So now the whole goal of modular is to break out of this sort of scaling trilemma, essentially. And it's something that I think essentially was not really solved until this new paradigm came about. And so the point is, the first step is, okay, rather than re-executing every transaction, we're going to leverage rollups, so fraud and validity proofs, to verify that the execution of the transactions is correct without having to actually do the computation ourselves. So that's the first step. So now you have a block. Now what you can do is you can have a quote lazy ledger, which was the original white paper behind Celestia, where rather than now all the nodes in the network don't have to execute anything, but they do still have to download all the data, right? So now if I do increase the block size, I'm still increasing the node requirements, meaning that I will have to have a bigger and bigger computer to actually stay up with the network. So what data availability solves is that now that we've gotten rid of execution, we want to make it so that you don't have to download the full block to verify that all the block data is there. Because basically, I forgot to mention, for rollup execution to be secure, you need to know, even if you can verify that there was no fraud or that the state transition was valid, you need to know that the data behind that was released. Otherwise, the whole security model breaks down. So, and this is actually, I mean, it's true of any blockchain. If even in a monolithic chain, if a block producer proposes a block, like he sends out the block header, he says, hey, please sign this, but he didn't actually release the transactions, no one's going to sign the block, because they're all like, well, dude, we don't know what the hell is in here. So how can we say that it's valid or not? So in a trivial way, that's how data availability is solved in monolithic chains. But the point is, we want to break free from that. And so what data availability sampling is basically a way of making it so that end users or nodes on the network, rather than having to download the full block, they just download a handful of chunks, random chunks. And because of this special encoding scheme, you can have a statistical certainty that the full block is available. So you could, let's say, download 1% of the entire block data, but by downloading 1%, have a 99.9999% certainty that the full block is available.
Gotcha. A lot to unpack. So maybe let's kind of, I think from the data availability stuff, I think it would be kind of interesting to kind of keep on like the node topic.
Yes.
So one thing I'm super curious about with the data availability, the data availability sampling for Celestia, are you doing that with full nodes and light clients? Or maybe let's start with like, what are full nodes and then what are light clients? And then kind of articulate what Celestia is doing for both.
This is amazing. And I feel like maybe I should have covered this before going into all this stuff about like data availability and whatnot, because one of the core motivations, like the modular paradigm for blockchains comes from a very deep place. And that place is that essentially it comes down to the question of like what blockchains are for, and like what is special about them. And at the end of the day, blockchains are tools for social coordination. They are sort of like this means of having a trust minimized sort of like environment where people can sort of like transact and build applications without having to worry about third parties. So it's like a peer-to-peer network it's like a peer-to-peer, like verifiable computing environment. So like whatever, it's like this fortress where, you know, whatever happens in that blockchain, you know, it's not breaking the rules. Like you sign up to the rules by like participating in the network, and you want to make sure that those rules are upheld, right? And the only way to do that in a trust minimized way is to actually verify the chain directly yourself. If I'm not verifying the chain myself, then I am delegating my trust to someone else who's going to say like, oh yeah, trust me, I checked, wink, and like, you know, this, I'm telling you, like no one's cheating, like everything's cool. But then you're falling away from what the original purpose of a blockchain is, right? So how does that relate to full nodes versus light clients? So in any blockchain, there's kind of like two sort of classes of nodes. And I'm not talking about, by the way, I also feel like the term node is overloaded because there's miners and then there's validators.
I mean, feel free to separate them as much as you want.
Yeah. So there's like miners and validators are what I would call block producers. So they're the ones who build blocks and basically run consensus to agree on which is the next block that gets added to the chain. And they are nodes, like they are nodes in the network, but there's also there are non-validating nodes. And those are just people like you and me who are running a node on their computer at home. Mm-hmm. And why would you do that? It's because you want to either interface with the network, sending transactions and basically be able to like interact, or also probably most importantly in my mind, to actually validate the chain yourself and make sure that everything is going well, because you can't, if you don't verify the chain yourself, then these block producers, the miners or validators, can break the rules without you knowing. So like basically every time when you're using a blockchain, you've signed up for certain rules. Like on Bitcoin, it's like, okay, well, the rules are no one can print money, and you can only spend coins that, you know, you have the private key to spend. Now, if no one's checking what the miners are doing and looking over their shoulder and saying like, okay, they're not breaking any of these rules that we all signed up to, then in theory, they could print money to themselves. They just like, you know, mint a UTXO out of nowhere and be like, yo, I got 1 billion Bitcoin. You know what I'm saying? And so we're trying to, the point of having a fully validating node is that you can ensure that the miners are not misbehaving. Because if they do misbehave, it's catastrophic. Like they break the rules of the network, and they can do literally anything they want. So having a fully validating node basically means that you, even though you're not participating in building the blocks or like coming to consensus on the blocks, you're downloading everything and you're verifying it yourself. And so if anything goes wrong, you're going to notice it and you're going to be like, well, I'm not going to get cheated by these guys. Like they're trying to pay me with money that they minted out of thin air. Like I know that that's not real, so I'm not going to get screwed over. Or like I see you're going to catch any misdoing essentially. And then so there's the fully validating nodes, which again verify everything directly themselves. And then there's this thing called a light client. And essentially a light client is a node. Basically there was this kind of like acceptance in the early days that not everyone is going to have enough computing power to run a full node. It could be expensive. It also might be hard technically to even set one up. It could take forever to sync one, like on Ethereum. And so instead of everyone, it was kind of not realistic for everyone to run a full node. So as a compromise, there's this concept of a light client where instead of validating the chain directly yourself, you just download the block headers and make sure that that is the accurate block header. And then you assume that that header is valid. Basically, you make an assumption that the block producers are majority honest, or some people say majority correct. But again, the issue, the danger with a light client is that if there is a dishonest majority, all bets are off. Like you lose every guarantee about that chain. Like they could, as I said, print money. They could send your balance to zero. They could, break everything. And so that's the key distinction. And so with the core motivation of Celestia and modular blockchains is that we want to make it so that everyone can fully verify the chain directly themselves. Everyone should be a first-class citizen of the network. And that's the future that we're designing for.
Awesome. And so in Celestia specifically, how are you kind of breaking down the components of like what nodes are doing consensus and then what are doing like the data availability sampling?
So Celestia is, within this modular stack, it does consensus and data availability together in one protocol, essentially. So when a new block is sort of mined on the Celestia network, it's added to the canonical chain. So that it's like consensus, the validators sign it. So you have this finality guarantee that the ordering will not change. That's consensus. And then on top of that, you have an ability as a node. Obviously, the validators are supposed to make sure that the block they're not supposed to assign a block that's not available. But as I said, if they're malicious, they could sign a block that's not available. So the beauty of data availability sampling is that a light client equivalent amount of resources, we call it a light node, can sample that block, and it could be like your smartphone, and it could verify for itself that the data is available. So the light, your phone essentially becomes a full node. Of course, we call it a light node because we're trying to emphasize the fact that it requires very few resources. Like, typically to get those kind of guarantees on a normal blockchain, you have to run a very beefy machine. Like if it's a Solana, it's like a very expensive, cloud computer, or on Ethereum, it's probably like a pretty advanced, like at home. I don't even think you can run it on your laptop anymore. But so that's what we're trying to go for. In fact, it's possible. So like several of our community members, Mustafa, have run Celestia data availability sampling light nodes on their mobile phone. Fortunately, you need an Android, so I don't have an Android yet.
iOS only.
Yeah.
Nice. And so just to make sure for everybody else, like the clear part, and correct me if I'm wrong, the biggest, advantage, or like Celestia's key innovation, was the separation of these individual stacks, but then also the ability for the light clients to act similar to full nodes to prove that the data was available on blockchain.
Yeah, and the other really interesting thing, there's like so many different benefits to this separation of consensus, data availability, and execution. And one of the cool things about these light nodes is that by sampling the network, they are actually contributing to the scalability of the network too. So, and that's where we can talk more about like this sort of like BitTorrent-like scalability property of a data availability layer like Celestia. But essentially, the more, it's kind of like this collective effort where the more people are out there sampling data, then the bigger the block size can grow. So like, that's the beauty of Celestia, is it doesn't have this finite block size. So it can actually grow as more users and more nodes join the network.
And are those nodes, just for me, are those the light clients that are doing the data sampling?
Yeah, it includes the light clients up until like any node essentially that is sampling.
So light clients and full nodes both do the data.
And also, so the other cool thing is that there's no, like any amount of sampling that you can do is beneficial. So you could, if you wanted to, you could download the entire block, or you could just download half of the block, or 1/10 of the block, or 1% of the block. It's like sort of in the same way that in BitTorrent, you contribute as much storage to the network as you have available capacity for. That's what you can do on Celestia. And then the more that people are sampling, then collectively, the bigger the block can get.
Interesting. And is that, from that data availability sampling standpoint, is that because there is more collective throughput, or is it just that those light clients and full nodes are providing more security to the network, allowing for the block size to be bigger? So
it has to do with basically the actual scheme for data availability sampling, which is that essentially one of the important things is being able to, let's say the blockchain the block, he allows everyone to sample it, or he allows you to sample it, but then he then takes it away and stops letting you sample more. You need to be able to reconstruct the block. And so if you have enough nodes who all sample random chunks, they'll be able to then gossip around the chunks that they each have and then be able to reconstruct the block on their own. So like you need to at least have a minimum number of nodes downloading a minimum amount of data to ensure against that attack, essentially.
Gotcha. That makes sense. So if you have 100 nodes and they each download 1% of the block, they can theoretically put that block back together in its entirety and make sure that that block is legitimate. Cool. Awesome. Maybe to transition slightly and we kind of touched upon it going into it on a high level, is like the scalability. And maybe just kick off from how Celestia kind of plans to scale, and then maybe after touching upon that, like speaking a little bit more to the throughput.
Yeah. So this is a really great transition. It's often mistaken, and I also made this mistake early on when I was getting into blockchain, where absolute throughput of a given protocol is equated to scalability, right? But that's a misconception. And in fact, they're very different things. Because again, so throughput is just basically what is the maximum number of transactions that this protocol can handle, essentially. But that doesn't, if you just maximize throughput without taking into consideration, will anyone actually be able to verify these blocks or like actually keep up with the protocol, then you're sacrificing decentralization. So again, this is where like the fully validating node thing comes in. So what scalability really is throughput divided by the cost that it takes to verify that throughput, if that makes sense. So like, if you, and you can see this in a lot of different places. So let's take Ethereum, right? They have a low throughput, let's say 15 transactions per second. But then the cost to verify that is, you just need a laptop. Now, if you think about Solana, yes, sure, they can process a lot more transactions, but they've also increased the cost. So in reality, is it more scalable? Slightly, because they actually did make some cool optimizations and like the execution and parallelization and whatnot. But they also, a big part of their scalability boost was just straight up increasing the cost to run a node. And so it's really important to make that distinction, because people will just be like, oh, well, my protocol can do 7 million transactions per second. And it's like, yeah, but like no one's going to be able to actually verify that. So it's no longer really a blockchain.
I like that definition. The amount of throughput divided by the amount or the cost that it takes to verify that throughput.
Exactly.
I like that.
Yeah. So real improvements in scalability don't come from increasing the node requirements. It comes from clever things like optimizing the execution environment, innovations like data availability sampling and rollups and things like that. So and so again, if you think about what modular blockchains do, not just the data availability sampling makes it so it's very, very cheap to verify the consensus and data chain like Celestia, but also rollups make it extremely cheap to verify execution, because all you need to verify the execution of a rollup is just a fraud proof or validity proof. Mm-hmm. And then, again, that's something that you don't need very much computational power to be able to verify those things. So again, a smartphone could both do the data availability sampling and verify fraud or validity proofs. And so, like modular blockchains don't just increase the throughput, they also actually dramatically decrease the denominator, the cost to verify.
Gotcha. And for like the phone example, is there certain requirements of like bandwidth or compute that would be required to like be a contributing node to the network?
being a contributing node to the network is, again, however much you can contribute, like how much you can sample and whatnot, at least on the data layer, that's how much you can contribute. But there will be sort of like, there is a function of how big the block is to how much bandwidth you'll realistically need to be able to sample everything. In terms of compute, I think it's going to be to verify fraud and validity proofs. I think it's going to be, well, fraud proofs could actually be more complicated. Depends on the rollup, but most validity proofs are pretty easy to verify, is my understanding.
Okay. Maybe we've touched upon fraud and validity proofs a couple times, and I'm sure we will as we continue this conversation. So maybe just in like your words, like articulate what a fraud proof is and what also is the validity proof and how those will help the blockchain overall.
Absolutely. So a lot of times I think of, if you really want a simple mental model for understanding how modular blockchains work, it's really the combination of data availability sampling and fraud/validity proofs. So the data availability sampling piece is, again, how you verify that the data is available. And also implicit in this, this node is knowing that the transaction ordering is there. So it's also following the consensus of the chain. But then that's just one half of the picture. Right now I have ordered and available data. But what I need to do is actually execute over that data. I need to like put those transactions into my state transition function, my execution model, and basically, update the state. Like, I send a transaction, I'm trying to pay you $5, and then it will take $5 from my account, put it in your account. And that's basically execution. Now, as I said before, in a monolithic chain, every node has to re-execute every transaction. And clearly that doesn't scale, because as more transactions are sort of processed in the same amount of time, you need to do more computation to keep up. So the rollups, the whole idea behind rollups is that essentially it's a way of knowing that the execution is valid without having to re-execute every transaction yourself. So how does it work? There are two sort of different approaches: the fraud proof, which is optimistic rollups, and validity proofs, which are zero knowledge rollups. So in the optimistic rollup case, as it sounds, you optimistically accept when you see a new sort of block header for that rollup, you assume that it's valid. You're like, I trust that this sequencer is this is the node that runs the rollup, is following the rules. But like, how would I catch them if they did something wrong? That's where fraud proofs come in. Is you assume that there's at least one honest full node who's watching the network and re-executing everything. So there is one guy that's actually doing that work, right? He's downloading all the data behind that rollup and he's re-executing every transaction. And then if he sees, hey, this dude, he posted this like new block that basically doesn't add up, like he didn't follow the rules, then he has a way of basically proving that happened. And he can send it around to all the nodes in the network and they can verify it themselves and be like, oh, okay, thank God this guy caught this guy trying to cheat. I'm not going to listen to that block. So that's the optimistic side. And then the zero knowledge rollup side is a lot more straightforward. It's basically that the sequencer, the person operating the rollup, when they execute those transactions, they also put them into a zero knowledge circuit that proves, it comes out with a succinct proof that this update that he just made is valid, and you can just verify it directly yourself. So they don't even need someone watching them. They just need that proof. They need to generate that proof.
So with fraud proofs and validity proofs, they're more, in another term, just an optimistic rollup or a ZK rollup. They're being posted back down to like Celestia, the base layer, or the...
So this is another confusing thing. So there's a lot of different options and it depends on the design of the rollup. But I think kind of the question you're getting to is, well, where do these fraud or validity proofs go, right? Who's in charge of like either verifying them or circulating them? And there's a huge design space for how you might set this up. But essentially, like, there's a few options. One is you could post it down to Celestia. However, Celestia does not have any execution on chain. So it can't verify a fraud proof or a validity proof in protocol. But you can post it there to make sure that it's available for anyone who wants to see it. So that there's that option. The next option, and I should also make a distinction. So in Ethereum is a monolithic chain as it is right now, and it actually has an execution layer built in. So rollups that are built on top of Ethereum today often will rely on Ethereum's sort of the EVM to post their fraud or validity proofs and have it be verified on behalf of users.
Yes.
That makes sense.
Yes. So like the rollup chain will post that data back down to the layer 1.
So rather than, essentially one way to think about this is rather than having, I could just verify. I have a computer on my phone. Everyone's got a computer these days. They could send me the fraud proof, and I could verify it on my own machine. Or I could have Ethereum's computer verify it for me, and I can just trust Ethereum that it's valid.
Gotcha. So there's this like distinction on where that is being posted or verified at the end state.
Yeah. So it's either, so when we say that someone in themselves who's running a node is verifying it, we say that it's being verified client side. Like I'm running a client of this rollup and it's verifying that proof. Or if we say that the fraud or validity proof is being verified in an execution layer, like Ethereum, we call that as basically like being like a settlement layer. Like it's Ethereum in that instance is being used as a settlement layer. Now I want to make it clear though that Celestia, you can build rollups like execution and settlement layers on top of Celestia. So if you want to build a rollup using this paradigm, there will be lots of options for you on Celestia because a settlement layer is just, again, another execution environment.
Gotcha. Interesting. So if you don't use so you have to use the base layer of Celestia, which is the consensus and data availability. And then you have a fraud or validity proof or optimistic or ZK rollup on top of that. If you don't use a settlement layer in between the data availability and whatever rollup of your choice, are you settling back that to Celestia, or are you just settling within that individual chain and just using Celestia as the data availability and consensus layer?
Yeah, so in that case where there isn't a settlement layer where you're posting these proofs to be verified, you would basically just distribute them in the peer-to-peer network of your rollup. So the fraud or validity proof would just get gossiped around, and your client would download it and verify it directly. So and that's important because it kind of draws a distinction between this idea of a sovereign rollup versus a non-sovereign rollup. And all that really is this rollup is it rely on some other rollup or another execution environment to basically for its security? Or is it more independent, like an L1, like sovereign, like its own blockchain? And so in the case where you're not using a settlement layer, we like to call those sovereign rollups because they're basically, though they are using Celestia for data availability and consensus, they are, for all intents and purposes, an independent blockchain.
Mm-hmm. And so in the independent blockchain standpoint, is it you're distributing or gossiping that data to all the other nodes that are running that like specific virtual machine?
Yeah. So rollups are basically like blockchains themselves, and any blockchain network has a peer-to-peer network, and so those nodes are connected in some sort of topology, and when a message gets gossiped, basically it propagates to every node in the network, essentially.
And my question here is like, if you have like, say, a EVM optimistic rollup on top of Celestia, when you're propagating that data, is it just to the other nodes that are also running that optimistic EVM rollup, or those nodes within that specific execution environment?
Yeah, exactly. So each rollup that, let's say, is built on Celestia is kind of its own network.
Yep.
But there's an overlap with Celestia insofar as they post their data and they read data from the Celestia chain.
Maybe, yeah.
And they're also all of those rollup nodes are also running clients of Celestia. So they're sampling and doing everything.
So maybe what I think would be super interesting for everybody else listening is like walk us through like from a user point of view, like I submit a transaction to Celestia and then just the entire stack, because then I think people mentally will be able to maybe follow a little bit through better.
Yeah, I feel like we should bust out the whiteboard for this. But let's start with I'm a user of a rollup, and I want to, let's say I'm just going to pay you $5 on this rollup. So I generate my transaction, I sign it, I send it to the network, the rollup network. It gets propagated around and everyone sees it. And then whoever the sequencer is, he takes that transaction and then he fits it into a rollup block and he executes it, right? And he updates the state of the rollup saying he deducted $5 from my account. Now your account has $5 more in it. And my transaction with a bunch of other payments or whatever people are doing gets turned into a block in that rollup. Then the sequencer would say, he would call up Celestia and basically say, hey, I have this block of data that I want to publish on Celestia to make it ordered and available, right? I want you to come to consensus on this, and I want you guys to ensure that this data was released. And he would sign basically what we call a pay for data transaction, where he would say, here's the data, here's how big it is, here's how much I'm willing to pay the Celestia network to include it in a block. Then that block, which again has a bunch of transactions in it, gets propagated to the Celestia network. And then the Celestia validators and nodes all gossip it around and they all see it. And then whoever is the leader and the block producer for that round of consensus in Celestia would slap that block in, that rollup block inside of a Celestia block, along with a bunch of other blocks of other rollup blocks. It gets confirmed. Then all these guys once it's confirmed, all these guys that are we're now back to the rollup network, they would sample that block and they'd be like, oh, okay, this block was available. They'd also make sure that the block is actually included in the Celestia block. And then all of a sudden they're like, okay, now I can trust that this is valid, if that makes sense.
That makes sense. So is the transaction final once it's actually been like disseminated across the Celestia base network?
Yeah, well, once it's included in a Celestia block, that's when you can consider it final.
Okay, cool. Very interesting. Just touching on the virtual machine or execution environment, I think could be interesting. I'm personally super interested in the non-EVMs, rollups or execution environments. As we kind of talked about initially, I think there's a lot of interesting design space to explore there. So maybe talk about Celestia's vision or future of how rollups will be included, and I think you already did, but maybe some interesting designs within the execution or virtual machine space.
Sure. Yeah, great. So I first want to frame this as going back in time a little bit and thinking about the evolution of blockchains over time. So we started out with Bitcoin, and Bitcoin was essentially, the simplest decentralized application you can think of. There's only a handful of rules, like we talked about. It's you can't print money out of thin air, and you can only spend money that you have the right to spend. And all of a sudden, that's enough. It turns out to have a decentralized money and payments system. The problem is that, as people started realizing, they're like, wow, this whole blockchain thing means we can, build other kinds of decentralized applications, right? But the thing was, in order to try to build a different decentralized application, you had to build an entirely new blockchain. So, things like Namecoin or Mastercoin or all these different projects, every time they wanted, or like Dogecoin, let's say, even every time that you wanted to build a new application with different properties to Bitcoin, you had to start a whole new network, right? And that's inefficient for a lot of different reasons. You got to get people to mine it. You got to, coordinate everything. You have to make it valuable. It's a huge amount of overhead to launch a new network. Then Ethereum came along and they said, okay, we see this as a problem. So rather than having everyone launch a new blockchain every time they want to build a new decentralized application, we're going to launch a general purpose blockchain where actually you can write any application and just deploy it as a smart contract. And you get security, you get shared security for free, basically because it's running on top of Ethereum's network. And then on top of that too, one of the best things is you get composability. So like all these applications can talk to each other. So that was a huge step forward in terms of being able to explore the design space for decentralized applications, because you brought the cost to launch a new decentralized application down dramatically, right? Now, taking a step forward, if we think about the drawback of that model is basically now everyone's stuck on one virtual machine, one blockchain, and you run into all these scalability problems. Now, the next step is modular blockchains. So rather than, and also I should start before going there. Now, like as each sort of blockchain, as like Ethereum reached capacity and reached its limitations, like people didn't like the EVM or what have you, they wanted to experiment with different kinds of models. People had to build new blockchains. So you got back to square one where you're like, okay, I want to build Solana. I want to try a different execution environment that has parallelization. I want to experiment with, more application specific blockchains like Cosmos. But you had to spin up new chains, new consensus networks each time. So that brings us, so we're back to that inefficient paradigm where it's a huge startup cost. Now in modular blockchains, essentially, we've made it so that you can actually spin up a new execution environment, a new execution chain, without spinning up a new consensus network. So again, our goal is basically to make it as cheap and easy to deploy a new blockchain, a new execution layer, as it is to deploy a smart contract on Ethereum. And I think by doing that, it's going to reduce the cost and therefore increase the experimentation of different execution environments. So that didn't answer your question, but I thought that was a very important thing, because it kind of shows this arc of development of blockchain over time and how modular blockchain fits in and is going to enable a new wave of innovation in execution itself.
So jumping off that, what are you personally excited in like the execution environment or virtual machine space, or what have you kind of seen starting to develop? Yeah,
there's a huge design space. So there's so many different things to play around with. And it's not just, so I'll start with one, which I think is kind of a no-brainer, is just parallelizing execution. So clearly, if, let's say I have 100 transactions and I want to compute them as quickly as I can to generate or like verify them. If I had to do it in serial and like one after the other, then obviously there's only so many that it's going to take me a certain minimum amount of time. However, if I can split those transactions that aren't dependent on each other, that don't impact each other, into separate sort of like work streams, I can verify way more transactions in a shorter amount of time, essentially, or even with less like computing power in some sense. Like you can tap into the fact that you can have multiple cores, and like basically that's a huge one. And Solana actually, I think, did a really good job of that. But there's other chains, something that I think is very similar, but has other like innovations on that same topic of parallelization is Fuel. So I really encourage people, if they're curious, to check out Fuel. It's funny, Ethereum introduced this idea of account-based blockchains, and Bitcoin was UTXO based, and Fuel actually, and it was kind of long thought that you couldn't do smart contracts in a UTXO based model, but Fuel has actually figured out a way to do smart contracts in the UTXO based model, and UTXOs fundamentally are extremely parallelizable because basically, they're all like, all the state is sort of self-contained in little containers basically. So ahead of time what they're like, each transaction is going to interact with a set of UTXOs. As long as those UTXOs are not overlapping, you can basically, verify separate transactions in parallel.
Yeah, I'm super excited for both Fuel and in general, kind of like the parallel processing. I think, as you mentioned, like it should be like a semi-obvious step as like for additional throughput. So I'm super excited just for the ability for people to create custom virtual machines or execution environments and play around with those different parameters and learn and see what works and what doesn't work. And so super excited about all that. No, it'd be very cool. Within those, I mean, maybe like continuing on like the execution and like virtual machine side, how do you kind of see like ZKs versus like optimistic, like combined with like the execution environment?
That's a really, really good question, and where things get very complicated, and frankly, what's possible is changing like every month practically. So there's the way to think about the difference between optimistic rollups and zero knowledge rollups is that in an optimistic rollup, the challenge is that you need to make the execution fraud provable, meaning that has to be easy for someone, with a small amount of resources to be able to verify when something goes wrong. And that becomes challenging because basically there's like one given transaction can, in order to prove that transaction is fraudulent, it could take it could touch a lot of state in the chain and could basically end up being very costly to verify the fraud proof. So you need to build execution models that solve that problem, or you need to build a method of doing of generating a fraud proof that solves that problem. There's been a huge amounts of progress there to things like Canon that Optimism is developing, and generally like this idea of interactive verification games that Arbitrum sort of, I think, pioneered are some really good examples of solutions to that. And I guess we could go like way more, like those topics go extremely deep. But there's also single round fraud proofs, which are a different model. But then, so that's the main, but the cool thing about optimistic rollups is that you can do more generalized computation on them because there's just like, you don't have, it's very much just like normal blockchains, except you're trying to make sure that you can do fraud proofs. Zero knowledge rollups are amazing because the benefit is that, as long as you can generate a proof to prove that it's valid, then everything else is fine. The issue is that making generalized sort of like computation fraud provable, not fraud provable, but it fit into like a ZK circuit is very challenging and still, I think, kind of an open research question. Although, again, there's been like massive like innovations in that even in the last like 6 months. So the problem with ZK is that basically you end up sometimes limiting the kind of computation you can do, or making it so that it's like you have to write a whole new computer language. So like this is what Starkware did with Cairo, is they just started over and basically said, the optimistic rollups are like emulating the EVM so that developers, or some of them, right, so that developers don't have to change anything. And then Starkware is like, well, we're just going to build like a sort of like execution thing that is designed to be Stark provable. But then the downside is like it's a whole new programming model and developers have to learn a whole new thing. But then the benefit is that it's like natively designed for that. So those are sort of like the trade-offs, I would say. And there's also the proving time thing and like the cost of proving on zero knowledge rollups, which can be expensive. or can be really like slow.
Makes sense. No, I'm super excited for it all. I like in my head, like I try to think of all blockchains, or I mean, in general, I think are relatively complex. Like if you didn't study computer science or distributed computing, like they're hard to follow along. But how I try to think of them, like layer twos in general, is like data compression back down, like trying to use the block space as efficiently as possible so you can propagate, I mean, say the same amount of data, but because you're using the block space more efficiently, you can propagate more transactions within a single block. And I'm super excited about whether it's optimistic or ZK rollups, or even just like the different virtual machines, like trying all the different avenues of being able to explore like increasing blockchain throughput overall.
Yeah. I think I like that. I like that mental model. I would say rather than data compression, it's more like compute compression, because at the end of the day, you still have to publish the transaction data to some chain, and there's limits to the amount that you can compress that part. But what you're really doing, the real magic sauce of rollups is the fact that you don't have to re-execute all these transactions. So like, that's literally what a zero knowledge proof is it's like a compressed computing. It's basically like, hey, look, this is the program that I ran and this is what I got. And rather than you having to run that program yourself and verify that this is like the correct output, just verify this proof. And fraud proofs are basically achieve the same result, but in a different way. Yeah,
no, I'm super excited about it all. Maybe kind of going down that like decentralized or compressed compute. I'm kind of interested on like Celestia's kind of like fee model, like kind of breaking that apart by like how do you guys like in Ethereum per se, like you're paying for gas or to be included in a block. Solana eventually is moving towards like paying for like a specific contract. How in like Celestia's design, like what are the fees? Is it like block model? Is it a state model? I'd love to learn more.
Good question. So Celestia is different from Ethereum or most monolithic chains, where in Ethereum, you pay for gas, which is basically, units of computational steps in the Ethereum virtual machine. And the more computation you want to run, the more you have to pay, essentially. And in Celestia, because there's no computation, it's literally you just pay in proportion to the amount of data that you want to put on chain. So it's like the fee will be like basically a price per byte of data is the way that it will work. Now, the interesting thing, and also Celestia plans to eventually, we probably won't ship with this, but eventually we will implement a fee model that mimics EIP 1559, because we think that's a really elegant fee model. Now, the interesting thing about Celestia, as opposed to monolithic blockchains when it comes to fees, is that you will not have the situation where once the block gets saturated, the fees spike. In theory, yes, the like a Celestia block could become full for a period of time, and the fees could start to climb. Like in any monolithic blockchain, because there's a finite block supply, there's a finite supply. As that supply gets used up and becomes more and more valuable or constrained, the price just has to go up, because it's the only way of basically allocating that resource. It's just supply and demand. Now, and so that results in this negative network effect, where even though, yes, more users and more applications on a given chain makes it more useful to more people, you end up also making it more expensive. So that's why I think monolithic chains always kind of run into this adoption problem, where once they get to a certain scale, it's like they can't really add more users, because it's just everyone gets priced out.
Unless they increase the like parameters.
Or unless they increase the block size. But then if they increase the block size, they're centralizing the network and they're compromising the whole point that they're there. Now, in Celestia, the interesting thing is that the block size is not fixed. So if it ever gets full, it can be increased. And it can continually be increased so long as there's enough people in the network sampling. So we won't have this negative feedback loop of like, oh, there's too many people using the chain, so everyone's getting priced out and has to go somewhere else. Instead, it's like, people use this metaphor for blockchains as like cities. And it's like, oh, well, Manhattan is super expensive because you can't make more land, right? But the beautiful thing about Celestia is that actually it kind of breaks that analogy, because essentially it's like maybe it's more like the frontier, like the US, where, the colonists were kind of over here, and then every time they needed more land, they just like expanded. So it's sort of a similar kind of thing where you can just expand and generate new land for people to build on as needed.
That makes sense. And in this scenario that like more users are coming on, more nodes are coming online, are you specifically increasing the block size, or are you increasing like the bandwidth in between nodes, or both?
Mostly increasing the block size. So I think what you're getting to is, as you increase the block size, does it increase the node requirements at all?
Does it increase, like, do you have to like up the bandwidth for the like node requirements to propagate more data between the nodes because the blocks are bigger?
Not necessarily. I mean, yes and no. So I don't think propagation is the bottleneck in increasing the block size. The main thing is that the end node, that end user that you want to be able to verify the chain, as you increase the block size, the amount of data that he has to download does slightly increase, but it's basically a square. It grows at the square root of the size of the block, so it's actually like really, really, it's sublinear essentially. So there's a slight bandwidth increase, but it's very, very minor, especially as the block gets bigger and bigger. That increase with each nominal block size increase gets less and less.
Gotcha. Very cool. Awesome. We've covered a lot. I think maybe just to recap, like overview, kind of started with like the modular versus monolithic and kind of like the key differentiators. In your point of view, those are the consensus layer, the execution environment, data availability. Was it the three, or did you have another one?
Consensus, data availability, settlement, and execution.
Settlement and execution. I'm curious, like out of those four, like what do you think, like maybe not for, Celestia, but like blockchains overall will be like the biggest bottleneck of like scaling blockchains?
That's a really good question. Well, at the end of the day, so any execution layer is kind of, they could keep expanding their block size, but they would eventually maybe reach a point where, that, like in theory, they're not really increasing the node requirements for someone to verify the chain, but the other assumptions, like there's one other honest full node, become more and more limited, right? Because like the block size is so big that there's so few people who can afford to run an honest full node that they might not do it. So they might not want to continuously just increase the block size forever. But what they could do, though, is it's basically free to just spin up another execution environment in parallel, and then those two rollups can basically have a bridge between them. So like I think, but there might be more sort of like I guess activity on one given rollup, and more people will want to like execute there. So execution within a given rollup could be sort of a scarce thing. But ultimately, like if you're getting priced out of a certain execution layer, you can always migrate to another one. And ultimately, no matter what, every rollup has to post back down to the data availability layer. So in some ways, the bottleneck for the overall throughput of the system will always be the data availability layer, like how much capacity that it has. But again, like there's a lot of nuance. It's like it doesn't fit into the standard model, if you will. For sure. No, I was just curious to what you think it will be, because I'm super interested in it as well. Awesome. So covered kind of the monolithic, tech stack, and also like the modular and the benefits of modular, going into like the difference of blockchain scalability versus throughput.
Also getting into like the execution environments, the nodes requirements from full nodes and light nodes, and then also kind of the execution environments, rollups, ZK rollups, optimistic rollups.
Yeah, we've done a lot.
Like the fee structure. One thing, and maybe like on a couple more things, we also touched upon the data availability and data availability sampling. Maybe just like a couple things to wrap it up. I'm super, as like the blockchain kind of grows from like state being posted to the data availability layer, where ultimately does that state get stored, and how is it stored in Celestia?
Mm-hmm. So one of the biggest problems, as people might be aware, for scalability of blockchains is not consensus, which is a massive misconception. It's actually state bloat or state growth. And it's a very nuanced problem, but essentially that is that like as more and more people use a given chain, the chain only accumulates state, meaning there's only more and more accounts or smart contracts that a node who's verifying that chain has to know about. And the issue is that as that state gets bigger, it becomes slower and slower to basically compute over that state. It's like a much more deep like technical conversation. And frankly, I don't understand all the nuances of it. Only like really, really smart like core people like on Geth and whatever really totally get it. But essentially, so that's one of the major bottlenecks of any given blockchain is that. So for example, that's why Avalanche can spin up basically a fork of EVM and run it a lot faster in the near term because they're starting from zero state, versus Ethereum can't run it faster because they already have a massive state. But eventually, like Avalanche will catch up and basically run into the same scalability bottleneck. No, Celestia thinks about this in a very different way as a layer one, which is that basically we want to have as minimal state on chain as possible. And one of the first things you do to minimize that is basically by excluding all execution. So there's no smart contracts. There's nothing that you can do on chain. There's literally just account balances. And that's basically it. Oh, and staking. Like you have to know who's staked how much. And that's it. So essentially, Celestia has been designed to push all the state and state growth and everything up to the execution layers. So the rollups are the ones that deal with that problem. And Celestia, essentially, no matter how big it gets, it will always have a very limited size of state because there is very little. It's just like literally, a ledger of who owns how many tokens.
Gotcha. So, and just to rearticulate, because the majority of the computational and state executions are happening on the rollup, and you're just kind of posting the data or the proof, whether it's an optimistic or a ZK rollup back down to the data availability layer, the total amount of data is just much less in general.
So it's not about so I think this is a really important thing. So state is different from sort of the transaction data in a given blockchain. So like each blockchain has sort of a state tree that basically is in every block, and it commits to basically what all the state is in that chain. But that state is not posted on chain. The only thing that's posted on chain is the transactions. So in Celestia, you can think of it as like the warehouse where all the transactions get posted. But the state itself is held on the nodes that are running the rollups themselves. So it's not about making the amount of transaction data less. It's more that that state is like the nodes that run Celestia, because they don't validate anything, they're not responsible for keeping that state. Each rollup is,
okay,
if you will.
That makes sense.
But this also kind of, maybe we should talk about this topic because it's also a common confusing thing, is the difference between, like storage and data availability. Like a lot of people think that, oh, well, Celestia is just it's just a database. Like, or why can't I use Arweave or Filecoin and post my rollup data there? And it makes sense because the term data availability sounds a lot like data storage. Essentially, it's like, oh well, it's available because I can store it on Arweave, but they're very different. Like data availability is not about storing your data. In fact, there aren't any guarantees. Celestia doesn't make any guarantees about the fact that your data is going to be around indefinitely. That's not in the same way that, Ethereum, just because you post data on Ethereum doesn't mean that that data is going to exist forever, right? Like the Ethereum protocol that makes no guarantees that like the transaction history will be around 30 years from now, right? That's an orthogonal problem to any layer 1 blockchain. So Celestia doesn't solve that problem. What it solves is, again, that problem of I need a way to prove to other people that data that I posted is available without them having to download it. And in Arweave and in Filecoin and these sort of like data storage networks, that's not the problem they solve. You can post data to Arweave or Filecoin or whatever, but in order to actually make sure that that data is there, I still have to go down and download all that data. So it hasn't made that problem any more efficient, if that makes sense.
I see. No, good distinction. Awesome. And then maybe kind of to like wrap it up, and then we can go into I don't know, more spicy questions. What are your kind of thoughts on like security as a whole, like shared security and non-shared security, and say the pros and cons of those different?
I'm so glad that you asked this because this is actually one of the biggest benefits of a modular blockchain design is that in addition to the fact that we make it easier to spin up your own chain, the chains that are built on Celestia, that share Celestia as this common consensus and data availability layer, they get something very special, which is called shared security. And essentially what that is it like there's the security models of those rollups basically have are sort of like overlapping in a way that makes it so that they can interoperate with in a trust minimized way. And on top of that, they're able to pool their security if you think about it. So like, if I spin up a new chain, let's say it's a Cosmos zone or a subnet on Avalanche, I have to actually get a bunch of stake onto that chain to secure it, right? And so my security is always basically bottlenecked by how much stake people are putting at risk. And then if you think about like that broader ecosystem, let's say we have 100 different Cosmos zones, they each have their own independent stake. Their stakes are all fragmented, so their security is all fragmented. And the problem there's two problems. One is, imagine if they could all pool their stake together into one big security layer, then they would all be as secure as basically the sum of all of their security budgets, right? So that you get that pooling factor, which is awesome, like network effect. And then on top of that, when those chains' security is fragmented, when they want to talk to each other, this kind of gets back to one of the fundamental like things in blockchain is blockchains, when they want to interoperate, they have to basically have some way of verifying what's happening on the other chain. Typically, and like the best in class right now that we have, like models like IBC, they all, and this is like ignoring completely most bridges, which are just basically committee-based bridges like multi-sigs. IBC is the sort of the best in class for now, and it basically says, I'm going to assume that any block that I receive from this other chain that is signed by the majority of validators is valid. But I'm not actually going to re-execute any of the transactions, because to do that is way too expensive to do on-chain. So what you're basically doing is any bridge now is between these two separate chains is assuming that the other validator set is majority honest. And as we talked about earlier, right, that's essentially like a light client in that model. Now, if that chain becomes malicious, they can steal funds from my chain. They could steal any funds that are bridged over essentially and do all kinds of bad stuff. So now when you expand that into like hundreds and thousands of chains, the likelihood that any one chain is going to be malicious or be insecure essentially is like gets very, very high. So in a shared security model, not only get this pooled thing, but each one of these chains, in the same way that rather than running light clients, which are insecure, you can run a full node, but with very light resources. These chains can actually run essentially light nodes of each other on chain. And so they're able to interoperate without making the honest majority assumption. So that bridge becomes ultra secure, where the other chain basically can't lie or trick the other chain into believing something that's not true. So they can't steal stuff. And all of a sudden it's sort of like a HTTPS, like you have like this secure sort of like a true internet of blockchains, but the connections between them are actually secure rather than the sort of this insecure, hackable, system that we currently have.
That makes sense. I definitely makes sense. I think, and I'll try to articulate it again. Like on a high level, in your opinion, the non-shared security is just ultimately a little bit more, it doesn't have, because whether it's a Cosmos zone or a subnet, they can be as minimal or maximum amount of state in each subnet or Cosmos zone. There's a wide variety, but in Celestia of like security guarantees. Mm-hmm. But in Celestia, just because Celestia is that shared base layer of the data availability, and you can use the light clients, with the majority or all execution environments posting back down to Celestia, that shared security is ultimately what makes it stronger than these other models, in your opinion.
Yeah, so there's two sides. One is the amount of stake. Everyone gets to aggregate their stake so that the overall network is more secure in terms of the consensus. Like you get stronger settlement assurances with each block. Then on top of that, you have the ability for these chains to, rather than making an honest majority assumption on the other chain when they want to connect with each other and talk to each other, they don't have to make an honest majority assumption at all. And
that would be like the bridges per se.
The honest majority. Okay. Essentially, yeah. Any bridge, unless they share a common data availability layer, there's a impossibility result, which basically says, unless you share a data availability layer, there's no way to interoperate without making an honest majority assumption on the other chain, essentially. So it solves that problem, and that's massive. If we want, like, imagine, think about it this way. Like, it's like, imagine if on Ethereum, rather than, when I launch a new decentralized app, like let's say I launch my own lending protocol, instead of being able to trust it out of the gate because it's built on Ethereum, imagine if it were just separate. And then not only do I have to trust that this application is this smart contract code is good, but the validators are also secure. So when I deposit my money in there, it's not like, I can't just read the contract and be like, oh yeah, I can tell I'm not going to get hacked. It's like, I also have to trust that whoever's running this app is not going to screw me over, right? And we take that for granted because we've been building on these monolithic Ethereum chains. But when we try to move into a multi-chain world, which we inevitably will, we will start to run into that exact same problem that I'm describing, where it's like, oh yeah, it looks like a great, chain. It's, everything looks good, but all of a sudden I have to trust the validators there. And that's just not a very scalable or secure way to go about things. Because
those validators don't have a lot of stake behind them. So their properties or the level of risk is higher.
Well, yeah. So that's a good point, which is that I also want to make it clear that we don't believe in there's only one chain to rule them all. We still think there's going to be what we call clusters, which is essentially there will be blockchains that are built on a shared data availability layer that can talk to each other in a trust minimized way, but there's still going to be independent chains that talk to each other. There's still going to be Bitcoin and Ethereum and a bunch of different Cosmos zones and whatever. But the thing is that inherently that system is limited to a much smaller set of blockchains, because those blockchains need to have a ton of economic security for those bridges to be secure.
For sure. No, and it makes sense. I'm just trying to re-articulate it correctly.
Yeah.
Cool. No, we've touched upon quite a bit.
I think one topic that I want to also mention before I forget about it is this idea of defining what modular blockchains are, because there is some confusion around like what constitutes what is it that like makes a blockchain modular or not modular, and there's especially this conflation of a modular blockchain and then modular software that is used to build a blockchain. So like one of the precursors to Celestia's idea of separating consensus and execution was Cosmos. Basically, the people who built Cosmos had a similar insight in that you can separate consensus and execution, but they didn't know how to do that at the protocol level. Instead, they did that at the software level. So they built software. They built kind of these two major components: Tendermint, which is just like a consensus protocol, an implementation of a consensus protocol, and then an interface, and the Cosmos SDK, which is basically these different modules that you can use to build like your execution layer. Mm-hmm. And it's really beautiful because by separating these two things, it makes it so that like, I can take Tendermint and then I can write a new Cosmos SDK app and just deploy it and plug it into Tendermint as like this sort of like, utility. So it did that. So there's that is what sort of this modular software thing is. And I think Avalanche is pursuing a similar model where like they have the Avalanche consensus and they have all these different kinds of execution things that you can plug in on top of it. However, when I launch a Cosmos zone or an Avalanche subnet, that chain is still monolithic because it's still doing consensus, data availability, settlement, and execution all in one chain, in one protocol. And same with subnets. Even though they're using modular software to build the node software, the nodes are still monolithic. The protocol is still monolithic. And so a really good rule of thumb that people can use to kind of identify the difference between a monolithic chain or a modular chain is that a modular chain on its own is basically useless. Like modular chains are only useful when they are combined with another modular chain. So like Celestia is a modular chain because all it does is consensus and data availability. And that on its own is totally useless. Like you can't do anything on Celestia. It's like, I'm just going to post data all day. Okay, well, who cares? Like you're not like there's no utility to that. Where it becomes where you get utility is you get a rollup to plug into it and run execution. So all of a sudden, with the combination of Celestia as a modular sort of consensus and data layer with a modular execution layer, all of a sudden you get something that's useful. Therefore, Celestia is a modular blockchain.
Nice. I like it. No, thank you. I'm super excited for everybody to listen to this conversation. Is there anything else? I maybe have like a couple of spicy questions I can just throw in at the end.
Let's do it.
Other things just while you're going on a high level. If not, we can go into spicy questions.
No, I think we've covered a lot, frankly. This has been great.
Awesome.
Let's do some
spicy questions.
Yeah.
My favorite recent spicy questions is just like surrounding the other chains and just like a couple pros and cons. So maybe like ETH pros and cons in your view. Maybe like if you could remove the modularity component, because I think those could be applied for, in your opinion, on like the vast majority of blockchains except for Celestia. So if you remove the modular critique out of like ETH, like what would you say is a pro con, like AVAX, like pro con, and like Solana pro con?
Good question. I think that Ethereum, the real benefit is frankly the network effect. I don't know that like the EVM is necessarily like the best execution environment, or obviously Ethereum is still running on proof of work, but they will transition to proof of stake. But like the network effect around the EVM with auditors and like tooling and developer support is super important, and also just the network effect of all the applications and users and value on Ethereum is really, I think, the main thing. And what's beautiful is that I like Ethereum because they're aware of this new modular paradigm, and that is basically their entire roadmap going forward, is basically to launch data availability sampling via dank sharding, and they have a bunch of rollups already being built. So I really like Ethereum, obviously, because they align with the modular thing. So sorry to bring the modular thing back into it, but like it's hard to ignore that, because to me that's the only long-term viable way to scale blockchains. And if people are interested, like read Vitalik's post on the rollup centric roadmap for Ethereum, or also his post on the endgame. And I think those are like really good way to understand from their perspective what that means. Solana I like because they, as I said, I mean, they optimize for something just totally different. Like, and I think they like philosophically they just disagree, but they don't. There's a really great debate actually between Mustafa and Anatoly.
I listened to it.
Yeah, so
I like it a lot.
It's really, really good. It's at the Modular Summit, which we did in Amsterdam.
It needs more views. There's only like a couple hundred views on it.
Well, I think it got a lot more views because we only released the newer. We had to cut up the video and then like repost it, but I agree, it still needs more views. But one of the things that kind of came out of that was like, we disagree with Solana's design because, as I said, they are okay with increasing the node requirements and making it so that fewer and fewer people can validate the chain directly. Mm-hmm. And then that makes it so that if someone captures a validator set, they're able to basically misbehave. So everyone that uses Solana is basically implicitly making an honest majority assumption on the validators. I think, and actually from recent Twitter conversations, it seems like Anatoly is actually trying to think about new ways of sort of like curbing that and making that less of a problem. So it's really cool because I like that the Solana team is very open-minded and pragmatic. And also, as I mentioned before, they've done a lot of really cool stuff around block propagation, the whole idea of shreds, and they use erasure coding in their block propagation. They do stuff like parallelization of the virtual machine execution. And I thought it was really cool how they're doing this pricing of transactions based on, like, rather than just kind of having this like big bucket where everyone who's trying to use the chain has to pay the same price. It's like priced on units of like, well, what state are you trying to touch? So if everyone's like all trying to mint an NFT at the same time, it's like, okay, you guys are kind of isolated and you guys are going to pay a lot. But the people who want to do their normal stuff don't get screwed. So I think, I don't know, I think there's a lot of really good innovation coming out of Solana. And on Avalanche, I really like the fact that they're pursuing the subnet thing. Because, I mean, I'm a big fan of Cosmos already.
We should throw Cosmos in at the end.
True, yeah. So, well, I mean, the thing that I like about Avalanche is kind of the same thing I like about Cosmos, which is that, they're making it super easy for people to build their own blockchains, which I think is a really good, I think, just really healthy for the ecosystem, and for now is probably the best way to scale until we get modular chains. But I think, and I like Cosmos because Cosmos probably more, like significantly more, because I think that they have really done a good job with Tendermint. It's an extremely robust consensus protocol that is powering now so many different chains, even chains that like you don't think of as Cosmos chains. They're basically using the insights of Tendermint or some flavor of Tendermint. Like Tendermint is to me really like the state of the art when it comes to like proof of stake consensus. And Cosmos IBC is also state of the art when it comes to interoperability. Like the team behind Cosmos was so prescient and like ahead of their time, like way too ahead of their time, frankly. And they're still not recognized, I think, for the kind of work that they did. My only gripe with Avalanche is essentially that the narrative that the consensus is the bottleneck for scalability is, I think, disingenuous because there's a lot of other problems like data availability or the state bloat thing and all that stuff. So that's and also the fact that Avalanche Consensus has some, I think, security problems around the fact that, because it's actually, I mean, it's beautiful like this. It's pretty crazy that you can have, a network where no matter how many validators in the network, in constant time, they can all basically agree on the block. That's seriously pretty magical. It gets over like this issue of all the overhead of voting, right? And in something like Tendermint, you're really limited on the number of validators you can have. Yeah. So like Avalanche has a really cool benefit that way. But the problem though that arises is that because it's just a probabilistic sort of like voting, like you're polling rather than like voting, you don't end up having what we call like accountable safety. So like in a normal proof of stake, one of the benefits of proof of stake over proof of work is that in proof of stake, if someone is being malicious, then you'll be able to know who is, like, if they're double signing blocks or trying to mess around with stuff, you can see like who did that because they signed a transaction, and you're like, and everyone has a global view of who signed what. So then, like, when you see someone, okay, they forked the chain, or they try to make two conflicting blocks, you're like, okay, well, I know exactly this stake double signed, and so I know to slash them. Or like, even if they're a malicious majority, even if we have to restart the chain, at least I know who is bad and I know who to cut out. And an Avalanche, unfortunately, as of now, maybe they'll make changes, but I don't know how you can make changes while still preserving this property. You can't actually know what the malicious stake is. And to me, that's really problematic and that's why, they don't have slashing, because I don't think you can't implement slashing if you can't know who's acting maliciously. So that's kind of, I think, an issue. And of course, again, like, it can still work, but you're giving up one of the main benefits and like one of the biggest, like, most important, I think, security features of a proof of stake blockchain.
Maybe briefly do a con of Cosmos, and then touch upon do a con of Cosmos, and then one follow-up question.
Okay, I think the only con of Cosmos is essentially, that it's still expensive to launch a new chain because you have to bootstrap a new validator set and proof of stake network and all of that, and the lack of shared security. Like, even though IBC is the state of the art right now, it's the best that you can do, I think, between two independent blockchains. If you really want to get to this scale of like thousands or even millions of chains in the future, like far in the future, this trust assumption that you have to make for interoperability with Cosmos as it is not, I think, very good. So again, Celestia, you can launch a chain without bootstrapping a new network, and you can have shared security. And I think those two things are really going to be like, they're going to turbocharge the Cosmos vision of like an internet of blockchains.
And I can't think of the last question. It escaped me. But overall, thank you so much, Nick. I've really enjoyed the conversation, and I know a lot of other people will too. So thank you.
Yeah, my pleasure. Thank you, Logan.
Appreciate it.